All right. So for today, what we're going to do is we're going to do as promised. So we're going to moving from learning the value of a policy to learning the optimal policy. So we're going to do this in 2 steps. So for today, we will be setting up the stage and we'll discuss in detail the case of K-armed bandits. Most of what we will discuss will be actually on the 2-armed bandits. And then for tomorrow, we will just introduce the general algorithm for state-dependent situations. So ramping up from bandits to contextual bandits to the general MDP. So that's the plan for today and tomorrow. And then on Friday, we will have, as usual, the tutorial on this part, that is how to learn to control optimally a system without a model. Okay, so we are, you remember, we're always in the model-free setting now. Okay, so let's briefly recap what we had from previous lectures. So we focused on the question of how can we learn, given a certain policy pi, which is chosen by the agent. We aim at computing what is the value function, which is, remember you, the expectation in this particular setting that we use, the expectation of the discounted sum of rewards, which we can write in this way, given that the initial state is S. Okay, so once more, in this expectation value, it's hidden the fact that this expectation is running over a sequence so a string of data, or a stream, as it's also called, in which there is an initial state. From that initial state, an action yeah, so an action A node is taken, and this according to our chosen policy, and as a result, a reward is obtained and a new state is produced, and this is due to the dynamics that is underlying our system, that is the transition probability, which is, as you remember, unknown to the agent. So the agent just observes this sequence of states, actions, new states, etc. Okay. So these rewards that are appearing here are produced in this sequential manner by interacting with the environment. And what we have been showing in some detail is that it's possible to obtain an algorithm which, just based on the sequential reads of this stream of observations, it's able to construct this vector of values v pi, approximations of this vector v that converge with probability 1 to the true value for a given policy. Okay, so and the way that this algorithm works is in general, so temporal difference learning. So the pseudocode for this is, in general, is just initialize your estimate v node with some vector. Okay, of course, the closest it is to the true value of a policy, the better it is. Then at each time step, what you basically do interactively is choose an action. Then, so this is a loop, so better, yeah, loop. Here, choose an action AT from the policy. Okay, so you observe your state. Okay, so more precise, even more precisely, the loop starts here. Let's make it proper. The loop starts here. So the first thing is that you observe state. Yes. So even better. Sorry for this. The loop starts here, and you initially observe your initial state as node. Then you pick an action according to your policy. As a result, you observe a reward and a new state. Okay, and then you define the temporal difference error, which is delta t plus 1 equals, sorry, maybe I can put that more comfortably in another row. The temporal difference error delta t plus 1 is defined as the observed reward plus gamma, your previous estimate at the newly observed state minus your previous estimate at the current state. And you remember that this temporal difference error can be interpreted as the difference between the observed reward and the estimated reward. So at any given time t, you can construct an estimation of what you expect to be the reward at the next step using your current approximation of the value function, and you compare it with the actual observation. And this provides you with the temporal difference error, which you use to correct your previous estimate. Then in general, you define an eligibility vector. Okay. Or you update better by some algorithm. Okay, so initially you have defined also some eligibility node. So you update it. Et, you get your eligibility at time, let's say t. Okay, by some rule. Okay, for instance, just to clarify the idea, e.g., Et of S is equal to just the indicator function of the state you have just detected for TD nodes. Okay, so it's either you update it if you have memory, which is the case in TD lambda, or you just define it as the indicator function for the current state if you are TD node. Okay, so here you fill it in with your own favorite choice of eligibility trace, which might be the ones that you saw in the tutorial, or there are many other choices that you can make. Okay, and then this is the time to update your estimate. Okay, and the way you do it is just your new estimate at any state S is the previous estimate plus the learning rate, which might depend on time. If you schedule it properly, it should. The temporal difference error, and then the eligibility at that time. Okay. And this loop ends until termination condition. So this termination condition could be the error between the difference between the previous estimate and the current estimate is below some tolerance defined according to some norm or whatever you choose. Okay. So this is this algorithm under the conditions under Robbins-Monroe conditions, which are, I recall you, that the sum of the squares, the series of squares of the learning rates must converge, and the series of the learning rates must diverge. Under these conditions, we have that V T estimate tends to the true V pi as t goes to infinity. And the way it approaches it, so the convergence rate depends on the choice of the learning rates. Okay, so in a way that we don't discuss, but it's not particularly complex or informative at this stage. Okay, so this is in a nutshell what the idea of temporal difference learning is. And today we would like to combine this with the notion of optimization in order to solve asymptotically the Bellman's equation in a much similar spirit. So just relying on a sequence of observations that we obtain by interacting with the environment, like this stream here, we would like to update our estimate of the value and concurrently update our policy. So change our policy at the same time as we learn the value of the current policy. Okay, so this is going to be some sort of running on two different rails and trying to keep up in a consistent way. But before we go there, let's just take a very, very simple example of how temporal difference learning works. This is even simpler than the one that you discussed at the tutorial. So this example serves two purposes. So the first purpose is just to a little bit demystify all the temporal difference setting, in the sense that making it extremely transparent in a very, very simple case. Of course, this doesn't mean that temporal difference learning is a trivial concept. It's a concept which, however, connects very, very clearly to some very, very simple idea. This is the first purpose of this example. The second one is because we refresh our ideas about bandits that we will be using subsequently. So the example that we discuss here, what is the value of a policy for a K-armed bandit? So a K-armed bandit is a very simple object from the viewpoint of MDPs. Okay, so there is just one state, a single state. What is it, this state for a K-armed bandit? Well, a state for a K-armed bandit means that we have K arms to choose with. Okay, so this is 1, 2, K. And each of these arms has some distribution of rewards. Okay. So for instance, for arm 1, the rewards might be just like this, distributed like this. So this is the density, the probability density of reward for arm 1. And similar, there could be different distributions for the arms. I'm drawing them explicitly in these weird ways to convey the idea that they could be anything. Okay. So it's a totally arbitrary distribution. We usually put some conditions of well-behavedness. So when you have to study algorithms for bandits, you often find the requirement that this distribution be bounded, in the sense that there is a minimal and a maximal reward, or that they are sub-Gaussian, which is a statement about the tails in case they are not bounded. So you will find many times this kind of assumptions. It's possible also to discuss bandits with broader distributions like power law tails or whatever. So you might be seeing many of this in the literature if you happen to be interested in this kind of problems. As well as there are many test beds which are much simpler, like Bernoulli bandits or Gaussian bandits. Okay, so they could be of any kind. Your lack of knowledge about the distribution could go from I don't know anything except that it has some nice boundedness property, or I could know that these are all Gaussians of the same variance, but I don't know the means. Okay, so all this defines one state. Okay, so the state here is how we parameterize the distributions of the various arms. Okay, and once we have that state, there are many actions that we can do. Okay, there are k of them, 1, 2, k actions, and for each of these actions, you inevitably get to the previous state, okay, which means that these distributions don't change over time or don't change as a result of the decision I make, which means that in practice we are dealing with a specific situation which goes under the name of stochastic bandits. Okay, and in this process of getting back to the new state, you get your reward, which is picked from this particular distribution. Okay, so if I pick it from action 1, I go like this. This means that I'm picking it from this distribution here, and so on for different decisions. Okay, so now we suppose that we fix the policy. What does that mean? It means, for instance, we might just to fix the areas, choose a random policy. So we pick actions at random. At every step, we roll a dice with k faces, and we choose which action to take, and then we observe the reward that it gives. And then our question is, what is the value of this policy, and how do I compute it according to temporal difference? Okay, so so in this case, what we come to observe is not a sequence of states, because the states is always the same, so it's absolutely irrelevant what we observe at the level of states, but we just observe a sequence of so we pull an action, we pull an arm, we get a reward, we pull another arm, we get the second reward, and so on and so forth. Okay, so yeah, here in there is a slight misalignment between the notation for MDPs and the notation for bandits, in that usually in temporal difference you define the reward as R sub t plus 1 to convey the idea that it depends on both the present state and the future state in general. So at least this is notation that Sutton and Bartow use and promote. For bandits, usually you use another notation, in the sense that if you pick an action A, you observe a reward which has the same time label as the action. So usually the stream here is defined as follows. Okay, so this might be a little source of confusion if you skip from one notation to the other, but just a little bit of reflection should solve the issue. Okay, so this is also a disclaimer that if I mess up with the notations, I can blame someone else for that. Okay, and then you observe this, and then you want to obtain what is the value of this policy that is generating these actions. Right, so now the value of a policy for a stochastic bandit is a very simple object, because since there is one state, v pi is a scalar. Okay, so it's just a real number. So we don't need to deal with the vector. And also, since there is a single state, there is only one meaningful choice for the eligibility, which is just to give one. Okay, so eligibility. So you cannot give credit to other states, because there's just that state. And there's no reason to give credit, different credits at different times, because all the processes are inherently stationary. Okay. And then, as you may recall from our previous discussions, gamma does not play any role. The reason is that we, at every time, we pick an action independently from the past, and we observe a reward independently from the past. So when we have a certain gamma, we basically, the only thing that changes is that we have a factor 1 over 1 minus gamma multiplying the overall value of the function. Okay. So you can see that from the let me open the parentheses here. You may remember that we have the recursion relation, not that thing, please. We have a recursion relation for the value. So the value of a policy, yes. So this object that you've seen several times so far. Okay. So for a bandit, remember, there is no state. So this is just a scalar. It drops, all the indices here drop out. This object here for a bandit is one, the indicator function of the state, which remains the same. So this is your policy, and your policy doesn't depend on the state. So we can just put pi of a. So if I use this recursion relation, this just tells me that this is equal to sum over a pi a of the reward, which again depends only on the action, plus gamma v pi. So I'm just been rewriting the recursion relation for a bandit. And then now you realize that if you open up this sum, this first term is just sum over pi a. Okay, these are the average rewards, remember. And then I get plus gamma. V pi doesn't depend on the action, it's just a number, so it goes out of the sum. And here I have sum over the probabilities of the policy. But this thing here is equal to 1, because probability normalized to 1. So you see, I can take this term here and take it to the left-hand side. And if I do that, I get that v pi is equal to 1 over 1 minus gamma sum over a. So you see that whatever gamma I choose, I always get a value which is proportional to the value with gamma equals 0. This is v pi for gamma equals 0. So it doesn't really matter to have gamma different from 0 for bandits. And like I told you, it's just because you're basically repeating the same thing over and over again. There's no change. There's no notion of a future in practice. Okay. So so far we can stick to we can stick to gamma equals 0. It doesn't make any difference. So all these simplifications are particularly useful because they basically break down temporal difference to a very simple algorithm, which just does the following. So TD, again, TD whatever, because it doesn't matter, eligibility traces can only be one, so there's no difference between TD node, TD lambda, whatever. TD for bandits. Well, this just tells you that your estimate at subsequent time is the estimate time. Now these are scalars, just numbers, plus your learning rate alpha t. And then you have your reward, which I now are using RT, minus. So this is what the temporal difference error becomes for bandits, for gamma equals 0. It's just the difference between the reward and the current estimate. Okay. Okay, now we can further unpack this recursion to make it even more transparent, to see what is happening here. And to do that, we consider two situations. So the first case is when the alpha t's are constant and all equal to each other. Okay. So we know that this is not a good choice because this is not going to give us convergence to the true value function, because, I mean, at least, okay, let me state it more precisely. The conditions, the sufficient conditions are not verified, so we cannot rely on Robinson-Monroe result in order to prove that this converges to the actual value function, okay? Which is a more precise statement to make. Actually, the only precise statement. Okay, so let's consider this situation. So let's just do this very pedantic way. So let's start with the guess and say that we choose 0 for our initial value. For just this is just meant to simplify the calculations, but you could choose any value. Okay. In fact, you don't know what is the distribution of your rewards, so it could be anywhere. It could be in the 1000s, and it could be in the -1000s. It could be around 0, whatever. You don't know. So you start with your 0 guess, and then you, at the first step, okay, remember that you have your stream. You pick an action A node, and this, as a result, gave you a reward R node. And then what you do is you update according to this rule with alpha constant, and then you say, okay, this is going to be the reward at my step 0 minus the v at step 0. But these objects are both of them are 0. So at my first step, I just get alpha times the reward that I just measured. Okay, so far so good. And then I go to the second step. And the second step tells me that I have to do v1 plus alpha, the new reward, minus the value 1. And then I have just to plug in this expression from the previous time. And this becomes alpha R node plus alpha R1 minus alpha R node, which I can expand to see that it becomes alpha R1 plus alpha 1 minus alpha R0. Let's do another one, just for the sake of being explicit. But you start seeing the pattern, I hope. And then it means that I have to use V2 here. And use V2 explicitly there, which will lead me to, and let's rewrite this in another way, which makes it even more transparent, I think. So I collected the estimate V2 in the previous line. Okay, I extracted this one here, and then I collected that. And then if I plug that in, what do I get? Well, I get alpha R2 plus alpha 1 minus alpha R1 plus alpha 1 minus alpha squared R0. Okay. And then you can proceed inductively, or you can just jump ahead and say that after t steps, your estimate will be like this. So this is going to be the sum t prime from 0 to t of 1 minus alpha to the power t. It's t prime r t prime. Okay, and you can check that this is indeed what is happening, or you can take this expression and plug it back into the recursion here, into this definition of temporal difference, and check that everything adds up properly. Okay. So what is temporal difference doing here with fixed alpha? Well, it's just taking an exponentially weighted, geometrically weighted average, and it's weighted with recency. Okay, recent stuff has a larger weight. Okay, so if you look at this expression here backwards, you see that your estimate at step 3 is alpha, your learning rate, times what you just got at time before, and then you get alpha times 1 minus alpha from what happened at 2 steps before, and then alpha times 1 minus alpha squared, what happened 3 steps before. Okay, and this is what is expressed here. So this is some sort of fading memory. Okay, it's a geometrically fading memory. So if you have your sequence of steps from 0, 1 to t, and you have collected rewards, which I can put as sort of points here. So this is my reward 0, my reward 1, etc. I get my reward t. Okay, let's add also a reward t minus 1, just for simplicity. Okay, so what this object is computing is that it is computing some weighted average of this object, which is weighted with some geometrically or exponentially, if you wish, decreasing kernel. So this object here is this 1 minus alpha to the t minus t prime. So, and you can see how these two extremes come to happen. If alpha, so for instance, if alpha gets exactly equal to 1, what is happening here? Well, your kernel is extremely short. It just cares about the current moment. In this case, your estimate will just be your instantaneous reward. Okay, so it relaxes immediately to what you just observed, which is a good idea if there is no noise, but a very bad idea if there's noise. In general, there is noise. And also, in a multi-arm bandit, the reward that you take depends on the action that you just took. So it has no memory whatsoever of all the other actions that you took. So alpha tending to 1 is not a good idea. Okay, it has its merits to get a large alpha because you converge rapidly to your value function. Okay, because this gives you the rate of convergence of the sum. All these many terms, if alpha is big, 1 minus alpha is small, and this sum tends to converge quickly to its average. But there's a but, of course, you have a lot of variance because these things may fluctuate. So you may want to see what happens when you go in the limit of alpha tending to 0. When alpha tends to 0, the good news is that you average a lot because you sum all these terms more or less in the same way. but you have to wait a lot before your curve eventually approaches your current value. Okay, so in a nutshell, what temporal difference with constant alpha is doing in this very simple setting, it's computing a running average of the rewards. So as they come, you have this running average with some exponentially fading memory in the past, and then you just keep on keeping track of this. So as such, it stays around the mean. You can actually prove that the average value of these estimates is the true function, which is a nice exercise. Prove that the expectation of Vt is V pi. So if you average over many, many histories of actions and rewards, this is exactly V pi. The key observation is that everything here is linear. So when you do averages, it's very simple. But you also can see that in this case, you can prove that the variance of Vt stays finite. This is the drawback of having the constant alpha. And you can check how does it depend on alpha. So the intuition is that as alpha goes to 0, the variance should go down. But you will also realize how long it takes to get there. Okay. Very good. Now, second situation, which is also of interest. Let's say that we take alpha t equals 1 over t plus 1. This is a choice which resembles the situation for Robbins-Morrow conditions, only that strictly speaking, this is outside Robbins-Morrow because it's just exactly on the border, and the border is not good enough. Okay. Yeah, I guess so. It's a situation in which your sum over alpha t diverges. No, sorry, it's inside. Sorry, it's just in the border, but it's inside. Okay, very good. So what does it mean to perform temporal difference learning with this choice? Let's rewrite once more the formula. And this would become 1 over t plus 1. Is this expression any familiar to any of you? No? Doesn't ring a bell? Okay. So if it doesn't, maybe what it would be is that let's repeat the exercise that we did just a second before. Now let's start with the v naught equals 0. Then we have our first choice, which will tell you that I have to put p equals 0 down. So this is r 0. Okay. So here I'm just replacing v naught here and here to 0. And then I'm taking r0 divided by t plus 1, but t is 0 here. Okay, so this is t equals 0. Okay, do you agree with that? Fine. Then let's go to t equals 1, which gives me my estimate v2, which is v1 plus 1 over 2 r2 minus v1. All right, so this is r naught plus 1/2. Sorry, why did I put r2? Because this is where I promised that there will be confusion, and confusion it is. V1, 2, so this must be R1. Okay. So this is R1 minus R0. But this is R0 plus R1 divided by 2. Should I go on? Can you guess what this will be? Anyone wants to try? So if I had one sample, I had this. If I had 2 samples, I got this. If I have t samples,
it's like the average.
Yeah, the empirical mean. This object is nothing but the empirical mean. It's the sum of the rewards from time 0 to time t minus 1 ri, sorry. One over t. And in fact, this object here is nothing but the recursive way of computing a sample mean. Okay, so I'm pretty sure you have used this in the past. When you compute a mean of data which come one after the other, okay, you don't wait to collect all the data and then you sum and then you divide, but you do it online. As data come, you correct your current sum by this, okay? Which is again another way of interpreting at a very broad and, if you wish, superficial level what temporal difference is doing. It's trying to compute an estimate, in which case this turns out to be exactly the sample mean. Okay, so you could do that by using a memory which fades out very slowly in time, like 1 over t, or you could do it with a memory which fades out geometrically in time, like this in this case. Okay, if you do it like this, you are guaranteed to converge to the mean. Why is that? Well, just by the law of large numbers. The variance will be killed like 1 over the number of samples if you do it like this. Okay, which is another way to understand what the hell is going on with temporal difference methods in this very simple setting. Of course, generalizing from this to the full temporal difference problem is not obvious. Okay, so that's why I put the general framework before and the example after. Okay, so you see just that this is one specific instance of our problem. All right, very good. So now that we have, I hope, come to the process of demystifying what the general idea of temporal difference learning is, and nonetheless understanding that it's connected with very powerful ideas like stochastic approximation, which in itself is connected with the stochastic gradient descent. Okay, so whenever now you encounter in your different excursions in machine learning the notion of stochastic gradient descent, just be reminded that there is a continuous path bringing you from the simple notion of how to compute a sample mean to gradient descent, and these are the steps that connect the dots. Okay, now we are ready now, really ready to start for the real endeavor, that is how to couple this kind of reasonings with the optimization. And we will do that for bandits, but for doing that, we will just need to enlarge a little bit what we've been doing so far. So add a little bit of a new angle on this, and then we're ready to go. But for that, I suggest that we start after the break, which could be, say, 5 past 10. Okay? See you later. All right. So the last ingredient that we need in order to set up the stage in full for tackling the problem of finding the optimal policy, at least for bandits today, is to recall that we've been working so far mostly with an object which is the value function of a state, but there is another important quantity, which is the value function of a state action pair. So And it shouldn't come too much of a surprise for you to know that you can learn the state action value function as well by the same technique. So just a quick reminder to what this object I'm talking about is. So we introduced it, the quality or state action value function of a pair of states and actions is just the expected cumulative return, and then, you know, already reverting to the general notation, starting from a certain state and a certain action. Okay, so there's a double conditioning here over the initial states and the action that is taken. This object is, in fact, by unrolling this sum here and extracting the first term and considering all the rest that happens afterward, it's easy to derive the following relationship. Between the state action value and the state value function. Okay, that's how the two things are connected. It's quite straightforward. It just tells you that if you start from a state in S and pick an action A, then this will send you with probability small p to a new state S prime here. And as a result of this state action and new state, you will collect an average reward, the small r. And from that point on, it will send you for a new state S prime. And therefore, what you gather from that point on is just the value function. Okay, so you have split the contribution of the action that you took at the initial time from what else is happening in the future. Okay, any question? There's also a converse relationship, which is also straightforward, is that the value function at a certain state, well, this is just the average over the actions that you choose of the state action value. Okay, so this is again mapping in the same language. So these two equations together clearly tell you that the value function and the Q function are totally equivalent, and you can trade one for the other. The advantage of the value function is that it's more compact. It's just a vector. And the advantage of the Q function becomes more apparent when one discusses things like the Bellman equation. Okay, so I will make it clear in a second. So just to complete the full picture and see the two things at work, one beside the other, the first thing that one has to realize is that if we combine these two equations together and we replace the value function here for its explicit expression, which is present here, then we can write the following relationship. Or too many parentheses. Okay, so I just replaced this last expression for the value function here. So this is a closed linear expression for Q, okay, which can be used for temporal difference learning, pretty much as we use the recursion relation for V for temporal difference learning. Okay, so this is the first message, and we will do that in a second. But let me just stress that there also is a Bellman's optimality equation for Q, which reads Q star. So for the optimal policy, this is going to be Converse prime. And the first part stays the same as always, plus gamma, but now we have the maximum appearing here. And this also tells me that the optimal policy from state S is to pick the maximum of my Q star matrix. Okay, so this is the equivalent of the Bellman's equation and how we derive an optimal policy from the solution of the Bellman's equation. And this is where the merit of the use of the state action value function Q becomes apparent, because this just tells you that if you know the Q star matrix, it's enough to look at all the columns. So for each row, which is labeled by S, okay, so let's say we draw the Q star as a matrix in which there are states here and actions here, okay, so all the columns are given by the actions and all the rows are given by the states. Then if you fix on one particular row and you select the column which has the largest entry, this will select the best action. Okay, this is what this formal expression above for the optimal policy means. You just by looking at this table, you just realize for each state, that is for each row, what the best action is. You just have to take the entry with the largest value of Q star. So the connection between optimal action and value function is much more straightforward for Q, at the price that you have to deal with a matrix rather than with a vector. Okay, so there are advantages and disadvantages here. But other than that, the two formalisms are exactly equivalent. Okay, there's no shaded area in which one thing doesn't give anything consistent with the other. In particular, you can also connect this with the optimal state to this relationship. So in this entry here is actually, he is also the star of S. So there's a perfectly matching dictionary. But we will come back to this later on. Now, for the moment, we just I just want to stress that given this recursion relationship here, you can derive a temporal difference learning for state action values. Okay, so given a policy, how do I learn what is the Q matrix for that policy? Well, it works pretty much like it worked for the value function. So there are some things that we already did. We have to move this left-hand side to the right-hand side and turn this expectation into a stochastic object. Okay, so we do not repeat all the steps because we've been doing that too far, but too many times. But I will just give you the bottom line, which is that you can update your Q function at each step according to a rule which is very resemblant of the one for the value function, only that there are two important changes. Okay, so the two important changes are that your temporal difference error here has a different form in the sense that it's constructed starting from your Q matrix values, of course, because that's the ones that you have at hand here. It's not the only choice, but it's the most straightforward one. And then the second thing is that your eligibility traces, now you have to give credit not only to states, but also to actions. Okay, so this is my eligibility.
Sorry, you're missing a T in the top right.
I'm missing a T. Yes, thank you. Okay. So from your stream of states, actions, and rewards, now you can construct this temporal difference error, noticing that you have to go one step further here with the action at time t+1 in order to construct this particular temporal difference error. And then you can use this to learn how to proceed. Okay. So let's go back to our example again with bandits. So with bandits now we have a Q function of pi which depends on the actions. So if you have two arms, this will be a vector with two entries. If you have k arms, it will be a vector with k entries. So how does temporal difference for Q work like? Okay, so this is TV node. Okay, so how does it look like? Well, let's do that explicitly. My new estimate for every A is my previous one plus my learning rate, step T. And then here I can use gamma equals 0, so I can get rid of this middle term here. And I just can say that this is just my reward, where again, there is this T+1, T-1, T+1, T ambiguity in the notation, but this is essentially what we get. And this again has to be multiplied times 1 if I pick the action small a at time t. Okay, so here is where there is this slight difference between what we've been doing so far, because what is happening now is that we update only the entry of our vector which has just been chosen. Okay. All the other entries, we leave them as they are, because this indicator function tells me you got a reward, and the action which is to reward, so sorry, to give credit to or to blame for this result is the action that you just took. Okay, makes sense. But if this is a result, you know that this means that while you're working out your strategy, you will have to keep multiple records, one for each entry of your vector, and you will be updating them asynchronously. Okay, so every time that you pick an action, you update that, and all the rest stays the same, and so on and so forth. So it will not come as a surprise that if you do the same kind of calculation that we did for the value function, but now for this situation, the formula turned out to be very similar, except that now you don't count time t, but you count the number of times that you have done that particular action. Okay, so it's easier written than said. When you use, for instance, your alpha constant, this will tell you that after t steps, if I'm not mistaken with again with the notation, or perhaps after t+1 steps, your estimate will be like, so supposing that you start with your initial guess always at 0, your final result will be that you have to sum over all t prime from 0 to t. And then you will have your alpha here, your 1 minus alpha here. But here, you remember we had the final time minus the current time in our expression here. Okay, you see, we had this exponent here. Now we have to replace this by the number of times that we have visited that action minus the number of times we visited the action at the previous time. Okay, so that's the only change that we have to make. So basically, times just flows by the number of times that I'm visiting. So every arm has its own clock, if you wish, which measures the number of times that I've been doing that action. So this is not expressing just that fact. You can work out the algebra. It's rather boring, not particularly informative, but the bottom line is that. And here you have your okay, doesn't matter. The intuition is always the same. You have different records for each arm. Okay, this n of t is the number of visits up to time t. So n of t is the sum of, say, I going from 0 to t. I hope I'm not messing up with the indices, but please check if what I'm writing is correct. AI is equal to 8. Okay, so this is just the counts. It's a random variable which counts the number of times that you have been doing that action, small a. Fine, whatever. This is just to tell you that the same things apply, only you have to do this in parallel in different records. And also you could define something which is slightly different. For instance, so this is the first situation. You could also use adaptive learning rates. Adaptive is in very, very limited sense here. So suppose you define your rate now dependent on the arm. So every arm learns at a different rate. And this rate is now 1 over the number of times that you visit the arm so far plus 1. Okay? So you have, for every clock, you have count the number of, sorry, for every arm, you count the number of times that you visited it. And you learn with a rate which depends on the number of times that you visited. And if you do that, you can do the simple exercise. You will see that your estimate QT is the sample average of rewards. This is, let's say, QT of A of rewards for arm A. Okay, so there is a parallelism here. If you do things carefully, you can map these things into sample averages as well. All right. So now we are more or less equipped with everything we want to proceed. So let's try to face the problem now of coupling all this machinery with trying to find the optimal policy for bandits. Okay. So what is the general idea that we have to deal with? So the framework that we have in mind is the following. So remember that if we have some policy, this policy can produce actions. And from these actions, we observe, in general, rewards and possibly also new states, okay, which lead us to an estimate of my Q, okay? So this is the sort of the flow that temporal difference learning proposes. You have a policy, produce an action, observe reward, update your Q, and then you start over again, okay? You do one of these steps, you update your Q, and then you start over again, and then you start over again, always picking action according to your policy pi. The general idea that we want to explore now is that we want to close this loop. So what is the idea? At every time step, you have a policy in your hands. Okay, so we're going to make this in time. So like from a certain policy pi at a certain time, we produce an action. We will observe a new states and the reward. We will use them to update our Q function. And we use this new update in order to produce a new policy. Okay, so we use our current information about the value function which we have at hand in order to improve the policy. Okay, so remember, this is what happens in the Bellman's equation. In short, you have a Q function, and from that Q function you derive a policy. Okay. This is also very resemblant of what we did with policy iteration. We had a policy, computed its value, and used it to improve the policy, and then computed a new value. Okay, so the idea is always this idea of cycling over, using experience, cycling, and improving. Okay. So, what is the a simple idea? For instance, we might say that if we have a certain estimate Q at time t, we may decide that we can pick our policy at time t as the argmax of Q at time t. Okay, so just again, now I fall back to the bandits situation. My policy would be the one when I pick the argument of argmax over. So I have one vector, which is my current estimates of what the qualities of each arm are, and I pick the one which has the largest Q. Okay, so once more, so think about this situation. I am using some policy, and I'm producing some samples for each of the options that I have. Say you have two arms, so I pull that and I get a number, and then I pull that and I get a number, and I go on and so forth, and I construct something which looks like the sample average of the two arms. And then at each step, based on which one looks better from the viewpoint of the sample average, I will stick to that. Okay. This is clearly dangerous. Okay. The scope, the goal of this part is just to show you how bad this choice is. Okay. So a simple idea, but too naive. So where does this idea come from? Well, it just comes from the Bellman's equation. Okay, that's what the Bellman's equation tells you. If you have your Q star, sorry, I'm going too far. Yeah, if you have your Q star, then you have your optimal policy just by picking the maximum. But the point is that, can you trust your current approximation? Is it accurate enough? Okay. So this is what you would do according to a so-called greedy choice. So how do we show that this is not what a good option would be? Let's consider the situation with k equals 2. It's a two-arm bandit. Okay? And let's assume that the rewards are positive. Just there's no specific need to do that. It's just for the what I will be showing in the following. Just graphically requires that the rewards are positive. Okay. So since there are just two arms, I can graphically depict my Q vectors. Vector in this on this axis. Okay, so this is component Q1 and this is component Q2. And let's assume that the true values, okay, remember here we are not Bayesian, there really are true values for the bandits. The true averages are somewhere here, let's say. So this is the average reward for ARM1 and the average reward for ARM2. Whatever distribution they have, okay? So they might be two Gaussians, they might be whatever, their means are there. And of course, we want to construct approximations of our Q that get better, but most importantly, they lead us to choose always the best one. And which is the best one in this case? So the best choice is ARM1, okay? Because everything that stays below the diagonal means that the ARM1 is better than the ARM2. Okay, so let's see how our greedy algorithm, what it does in practice. Okay, it starts from somewhere. So the first thing that we have to do, we have to pick up some value to start with. Okay, let's just for the sake of just to clarify things, let's start with one choice, and we will do many of those. So let's say we start here. So this is a choice which looks like already very well informed, okay? It's just like someone is whispering at your ear and saying, listen, ARM1 is much better than the other one, okay? Okay, fair enough. Let's say it's a possibility. Maybe we are just being lucky and we'll be starting from a good choice, okay? We will explore many of those, okay? This is just one to start with. So if you start with that choice, the first step, you just are greedy, and what do? You play ARM1, right? And if you play ARM1, you will update Q1. So you will make a step in this direction. Expectedly so, because it depends on the variance of your rewards of the first arm. Okay, so, and then you just may move around and so on and so forth. But eventually you expect to be converging here. Notice that you never pick the action 2 here, never. There's no reason whatsoever to pick it. So you will keep on playing action 1 and you will converge to some point which is close to mu1. So you will learn, of course, you will learn the value of ARM1, which is your best arm. So good. As a matter of fact, in this case, you're playing optimally all the time because you've been playing the best arm since the beginning. So no problem whatsoever. Now, let's see what happens if you play starting from another choice. So for instance, now okay, now let's do the fair stuff and let's say what we've been doing until now. So let's start with 0. Okay. And since we start with 0, now we are totally indifferent. There's no preference. Both entries of my Q vector are the same. So I could choose one or the other. So let's say by chance I choose Q2. Okay. If I choose Q2, well, my mu2 here is much above. So reasonably speaking, this will go up. And I find myself in the uppermost part of the graph. Okay. What do I choose now? Well, I choose action 2 because I'm in the upper part of the graph. And so I will go on and play action 2 all the time. My estimate for action 1, which is and could have been way better than action 2, is staying at 0 just because I don't visit that, right? So I go here, I learn perfectly well what is happening for arm 2, but the fact is that I don't get any money at all here. I'm losing money. Okay? So I'm collecting information about the wrong thing. So we could start from some other place, okay? For instance, let's suppose we start up here. Sorry, this is not a good place. Let me put it even better. For the reason will be clear in a second. Let's suppose we start up here. Okay, now also the situation seems to be somewhat dangerous because we are in the upper left part. But when we start doing things here, the nice thing that happens is that my estimate goes down. I'm playing arm 2, and then I cross this boundary. Okay, and then when I cross this boundary, I start playing arm 1, which allows me to converge here. And in this case, now that then I get stuck into the group. So you see that the bias, so the value from which you start, becomes very important. So all these are sketches which are admittedly very bad. The real situation when the variances are large are richer than this, of course, but this gives you the idea. If you are greedy, the initial bias can kill you. Okay. So in fact, there is a full picture for this, which you can verify independently. There is a whole region of points which is depicted here in dark orange. Including the axis. So all these choices here so if you start anywhere inside this orange area, you stay stuck and you never be able to reach the optimal decision, that is to choose arm 1. All the other points manage by one way or another. In doing so, they give up getting information about arm 2 at some point, so that they sort of all converge to the so all other points converge to this to the axis here, somewhere along this axis at different levels depending on where they started from. Okay, none of those necessarily gets the right value for arm 2, but it doesn't really matter because they perform all optimal. But of course, this is not what we want. This is extremely bad as a decision-making process, because we want to get to do the right decision with high probability. Eventually, we would like to do that all the time. So is this possible? Can we, there are many questions that arise. Can we devise an algorithm that does that in a finite time? So after, can I construct an algorithm that tells me that after a certain number of steps, I will be playing the best action with probability 1? Is it possible? Spoiler, no. Is it possible to have something slightly less than this? So is it possible to have something that approaches asymptotically decision making, so that the probability of picking the wrong arm goes down to 0 with time? Yes. And how fast? So how fast can I approach my optimal behavior? Okay. All these questions are answered mathematically by the theory of multi-arm bandits. So there are books about it. Okay, so we have no hope whatsoever of being able to cover a large part of that. But what I want to give you today is that first, give you a first hint about how to fix this problem. which is very general and applies also to the more complex setting of reinforcement learning, so including states, first. Second, I would also try to give you an idea of what are the limits. So what is not possible and what is possible, and what are the limits given essentially by statistics on performance on decision making. Okay, these are the two things that I would like to give you in the next 15 minutes. Okay, so a better idea. So what was the problem here? Let's discuss it in a very informal way. So the problem is that we are working in the wrong mindset, right? So let's try and think about a true decision-making problem. Like there is a teacher, and this teacher has to decide whether a student is a good student or a bad student. And then this teacher gives some assignment, then receives the assignment, and then it has to make the decision whether to fail the student or not. And this clearly is a one-shot problem in which the teacher is in a very bad situation, because there might be various reasons for bad performance, right? So that particular day, the student might feel bad, might have a problem, might just, it just was the only question that he didn't look carefully into. Okay, so there are many sources of error. So a better strategy is, let's repeat these things many times. So let's not just give one assignment, let's give 10 assignments. And then after that, we can make a more careful evaluation. Okay. But it's also true that you don't want to give 1,000 assignments before deciding. Okay. So as time goes by, you make your own idea about the student. Okay. So this very simple idea means that one has to balance the need for exploitation, that is based on the current knowledge. How much can I make a decision? And the quicker I make it, the better it is, of course. But at the same time, I don't want to kill exploration. That is, I have to allow for the possibility that since there is randomness in the world, things might happen just out of bad luck and not because there is a causal relationship. In a world which is perfectly deterministic, once you see an outcome, that's it. If you repeat the experiment, it will again give you that outcome if the world is deterministic. But if there is randomness, that's not the case. Okay, so we have to confront with statistics, with uncertainty. So good news for you students, because I will try to explore as much as needed. Okay, so but how to do it? Okay, a better idea is just to mix in some exploration to the previous idea. Mixed in, not more, but just some, because there's no. Okay, so mix in some exploration. How to do that? Well, one simple recipe, for instance, would be, let's define some small parameter epsilon comprised between 0 and 1, which we're going to call our exploration rate. And let's say that our policy now is at every time is the argmax of my estimate QT with probability 1 minus epsilon. Okay, almost always, in a sense, almost means depends on how small epsilon is. I will pick what my current knowledge suggests. But from time to time, according to this epsilon, I will pick any action at random. Okay. So if I repeat my experiment here, let's start in a situation where we were stuck, for instance, right? So I'm gonna draw this in red. So we were supposedly stuck here, but then there is this small epsilon. So again, at the beginning, suppose epsilon is I don't know, 1/1000. Okay. So roughly speaking, for the first 1000 steps, I will be repeating what I always do. Okay, so I will be playing only arm 2, and then I get stuck here. But then sometime I start playing action 1. And therefore, this will cause me to very slowly crawl in this direction until I cross this magic point here, and I start playing action 1, and then this finally accelerates and gets here. So this little noise that I'm putting into this walk in my queue space is enough to let me cross this point. Okay, so we're done, are we? Not quite. So what is the problem here? So 1, good. We are not stuck any longer. The bad news is that we keep on exploring, okay? So we will still do once every 1000 steps the bad thing. And cumulatively on the very long run, this is going to cost us. So again, here you see there is another tension, okay? So bad. This is still too much exploration. So what we would like to do, in fact, is the following. We would like to explore more when we don't know things and less when we know a lot. So one way out would be, for instance, let's explore more at the beginning and less at the end. Or let's explore more when we have been sampling this action poorly and explore less when we have been sampling this action a lot. Okay? So we have to find out a way to balance these two things. Okay, an even better idea. Let's schedule the exploration rate. Okay, so let's decide how to change the exploration with time. So for instance, at the beginning, we can set epsilon 1 at the very first step. What does it tells us? Well, if we set epsilon equals 1, we just take actions at random, no matter what our queue is. So it's a way of ignoring the bias, if you wish, and moving more randomly. So at the first step, if epsilon is very large, there is no such thing as staying in place. You just start moving around. And if the learning rate is also large, you will make large steps. So if you combine large learning rates and large exploration, your point here is basically moving around randomly. So you explore a lot. But as time goes by, you would like to, 1, make a smaller steps, which means alpha going to 0. Second, explore less, because you will be focusing more and more when you're close to the target, and you don't want to wiggle around. Okay? Fine. We know how to schedule the learning rate. But how do we schedule the exploration rate? So what is a good choice for decreasing epsilon in time in order to find the best choice? Okay. So here things become extremely interesting, and there would be a lot of maths to do in order to prove the statements that I'm going to give you. So we are not going to do that. I will just summarize the results and give you some insight on what the problem is and how to sort of get a qualitative understanding, semi-quantitative understanding of what is going on. So the key idea here is the following. Suppose that in our 2 arms bandit, okay, so we have a true value mu1 and a true value mu2 here, okay, and these things here is called the gap. After a certain number of trials, suppose that I have played this action mu1 many times, so I have a distribution of values for my possible Q1. Okay, so if I repeat these experiments many times under a certain choice of the policy, it doesn't matter, under any policy which is I don't know, under epsilon greedy. Okay, sorry, I forgot to tell you that this quantity here, this is called an epsilon greedy choice. Okay, because it's greedy but with exceptions times epsilon, chosen with epsilon probability. Okay. So as a result, I'm applying my epsilon greedy. I play many times the action Q1, and I play, because my algorithm is working properly, I'm going to play the second arm much less than the first arm because it's suboptimal, which means that I will have a distribution which is much broader. Okay, because the variance of the Q is just goes like 1 over the number of times that I've played that arm. This is the variance of arm A, goes like 1 over the number. So this just like the variance of arm A. This is the variance of the rewards, and sorry, this is the variance of the rewards, and this is the number of times that I visited that arm. If I make many visits, I will have little uncertainty. If I make a small number of visits, I will have larger uncertainty. Okay. So the dangerous events are the events that are here in the tail of this distribution for Q2. So those times where after this number of times that you have visited the, say, N1, N2, these are the number of visits to arm 1 and 2, or the number of times that you've chosen them. So this tail here is the dangerous one. So what is the probability of being there? So what is the probability that Q2 is actually larger than mu1? Because this is the situation where you would be wrong according to the greedy strategy, and this is the one that you want to kill. Well, this goes, I mean, for Gaussian distributions, this goes like exponential of minus the number of times that I played arm 2 times the gap squared divided by 2 sigma squared. So it goes down exponentially with the number of times that you visit that arm. So in order to kill this probability, you want to have N2 large. But to win, you want to have N2 small. So there must be some sweet spot in there in which you balance these two things. Where is this sweet spot? Well, when you take, when you keep under control this green tail of the distribution, but not too much. You don't want to make this distribution Q2 very, very narrow because you don't care. Okay, so this is one very important conceptual thing to bear in mind in decision making. Information is not the goal. Okay, the goal is to gain rewards. Let me do a very, very simple example. Suppose I tell you, you have option A, and under option A, you win 0 or you win 1 with certain probabilities. And then I give you option B. Under option B, you gain 0 or something which could be anywhere between 0 and minus 1 million. Okay? So, what do you choose? Option A, right? But option A is characterized only by 1 bit of information, whereas option B has an enormous amount of information. If the variables are continuous, there's strictly speaking infinite information there. But you don't care because this information has no value for you. Okay, so information is necessary, but only the bits of information that are important. Notice that information theory itself does not have in itself this notion of how much a bit is worth. Every bit is a bit. So decision making and information theory have a boundary, but one has to be very, very careful about what that is. So maximizing information in decision making might be a very bad choice. So you don't have to be curious, too curious about bad things when they are statistically reasonably bad. Okay, so that's where all the subtlety is. You need to collect information in order to be statistically confident that that option is bad. And once it's bad, you don't have to be curious any more than this. Okay, that's where the sweet spot between exploration and exploitation is. I'm talking like a guru or new age guru, so I better stop here and go back to the math. Okay, and the math tells you that this sweet spot is located when this N2 goes logarithmically with time. Okay, so this requires some elaborate math, but it's clear that N2 must grow. So the number of times that you visit some suboptimal arm must grow in time, because if you stop visiting, then there still is a small probability that things can be different from what you observe, even if it's exponentially small. So N2 must grow, but it must not grow too fast. And it turns out that the sweet spot is to make it grow logarithmically in time. And the precise statement for this is actually called the Lie-Robbins bound, which I don't remember from which time it is, but I think it's in 85. Okay, I have it here. 1985. Okay, so quite comparatively recent with respect to the age of the problem of multi-arm bandits. The Lie-Robbins bound tells the following, that the expected number of times that you play an arm A, if A belongs to the suboptimal choices, okay? So you have a K arm bandit and you pick an arm A, which is suboptimal. This is the number of times that you played that arm up to time t, and this is the expectation. And you divide this by the logarithm of the number of times that you've played, say t here, and you take the limit for t going to infinity. This quantity here must be above 1 over the Kullback-Leibler divergence between the distribution of the arm of the suboptimal arm and the distribution of the optimal arm. So this is, remember, the PDF of rewards for arm A, and this is for the best arm. So there's a lot here to unpack. So this is an asymptotic statement. Okay, this condition must be met for any policy such that the policy pi t asymptotically gets the argmax of the true values. So for any policy that asymptotically chooses the best arm with probability 1, that is a good policy, so to speak, still you have to pick the suboptimal arms at least logarithmically in time. And the prefactor of this logarithm is something which is connected to an information theoretic object, which is the Kullback-Leibler divergence between two distributions. For Gaussians, the Kullback-Leibler divergence becomes the delta square, the gap square divided by the variance. Okay, so you sort of can connect with this kind of arguments that I had above. Okay. So, of course, deriving this formula is not very difficult, but it will require 2 hours by itself. Okay, I will point you to a book which works and elaborates on this on bandits, where you can find all the mathematical results if you're interested. But the basic thing is here that this is the quintessential bound when it comes to balancing exploration and exploitation. It tells you that you have to keep on visiting apparently bad options. Okay, you cannot stop exploring, never. You should go on and on, but at the smallest acceptable rate. Okay, which means that cumulatively you must be logarithmic. The cumulative number of times that you visit a bad option must be logarithmic. What does it mean for the epsilon greedy? This means epsilon t going like 1 over t. Because if you pick the bad action every time step with probability 1 over time, when you make the sum of overall these probabilities, this will be the expected number of times that you do the wrong thing. It will be logarithmic, because the integral of 1 over t is the logarithm of t. And here you have to be careful about what you put here. So if you put exactly something with like 1 over t, you have to be careful, because if your prefactor is too large, it's fine, but if it's too small, you may fail. Okay. All right, I've been overflowing, so very last message. You can do even better than this. You could do something adaptive, like your learning rate could be depending on the action, like 1 over the number of visits. Okay, so this combines the idea of adaptive learning rate, adaptive exploration with the number of counts. Okay, so you can also adapt exploration also that the learning rate. And then there is a whole world of algorithms that we don't discuss, okay? Sorry, I think that's not the correct title. So the go-to reference for this is bandit algorithms by Latimore and Sepesvari, which opens up the discussion to all current knowledge up to, I don't know, maybe 1 year ago, 2 years ago, about what we know about bandit algorithms from the algorithmic viewpoint. Okay, I will post you a link to this book on the Slack channel. All right, so we're done for today. Tomorrow we will see how to combine this idea, epsilon greedy, with temporal difference learning and other kinds of exploration in order to produce good algorithms that find optimal solutions of the Bellman equation without knowing the model. Okay, fine. So if there are no questions, I'll stop sharing and see you tomorrow. Bye-bye.
Bye, see you tomorrow.